Our last talk for today. Ilya Goldschei from Queen Mary University will speak about non-Hermitian Anderson model on a strip, properties of eigenvalues and eigenfunctions.
In a sense, yes. I will be talking about a model on a strip.
No, one should somehow adjust.
Yeah, no. Yeah, I'm sorry.
There is maybe magnification.
No, it's no problem. I'll adjust it. So there is no question about that. Let me put it first of all here. No, we need adjustment there. And the models I will be discussing, there are several of them. And I will try to review the situation with these models. Where is this thing? Right. And they were actually discussed here today by Brian Davis. I will concentrate on the situation in a finite box. In other words, I will talk about the properties of this equation. G is a parameter, real, non-negative. And this is the so-called non-Hermitian Anderson model introduced by Hatano and Nelson in essentially 96, but the paper was, well, it was on archive in 96, and then it was published in 97. And they found some interesting properties of the spectrum of this model, which were discussed here. I will go back to that in a second. In fact, I first saw this problem when I looked at this model. Without any specific structure like that, when you have positive elements there, which is absolutely essential for the properties of the model. But if you have something like this, then what really happened before Hatano and Nelson, I'll try at least, actually looked at their model, or introduced their model rather, is this thing. Can you see it well? I mean, no, from here, certainly from there, I'm not sure. Okay, let me do it differently. I'll put it here, so that certainly can be seen well. So these are the eigenvalues of this matrix. 900 by 900 matrix. Just, yeah, so the entries here are IID random variables. Here. They are IID random variables, tridiagonal matrix. You have zeros. Otherwise, it's not essential. But what is essential is that they, say, are Gaussian, or they are distributed uniformly on -1, 1. And then that is what you get. This picture actually was produced in Bochum way before I saw, or we saw, rather, the paper by Hatano and Nelson by a student of Werner Kirsch. I don't know whether Werner remembers that. He does, okay. He has still a good memory. I thought at that time that that this picture, as a numerical analyst would have said, clearly shows that there is a limit. I don't know how you can clearly show it in this way, but that's what numerical analysts say. And indeed, there is another picture produced by this guy, a young man who has disappeared from mathematics, quite rightly, because all what he did was to put it on a computer. This is the distribution obtained experimentally, the distribution of the real eigenvalues of this model. But what is not presented on these pictures, so these are, you can see that they are there, but in order to see really what is happening on the real axis, you have to look at this. And this seems to be converging somewhere. What is happening there is a slight puzzle until now, and I will explain what I mean by this. If you have, say, I remember figures for 800 by 800 model. So he took a matrix 800 by 800, considered the eigenvalues, 800 of them, 408 in one experiment, where if you have a Gaussian random variable there, 408 of them were real. In another experiment, 412. So I never saw a figure which is below 400, but you can easily believe that if they are Gaussian, so this is a hypothesis, if they are Gaussian, in the limit it will be exactly a half. So this is the first open question which I will immediately tell you which is there. And it is not clear how to do that. Why there is this the existence of the limiting distribution in principle we can prove, but to understand how many exactly are there and why for a Gaussian random variable it will be exactly half of them, which is not the case, of course, for other distributions. Again, as numerical simulations show, this is still a well-opened question. Yes, sure. There is obviously a delta function on the real line, and it is of strong positive. It's a strong positive component of the whole measure, obviously, right? So the number of eigenvalues here is the same roughly as there on the real line. Of course, anyway, we were trying to do something about it, but somehow it didn't work until finally. By the way, it's not a very surprising picture. You somehow expect that something like that will happen, and it's not very surprising that all these, you have a lot of complex eigenvalues, and they are somehow distributed all around the plane. It's not very surprising. But what was surprising, and this is what actually prompted us to think about it much more seriously, was this picture. You see, these are not curves, if you want to know. These are dots. This is simply a picture on which you see 2,000 dots plotted by a computer. They simply take, this time, this model, the first one there, or this matrix with these entries in the corners, and you suddenly see this picture. So this contrast between these two pictures was really amazing. The more that I knew immediately that, in fact, in the limit, the operator which was discussed today in detail, you will have the whole thing covered with the spectrum, but you don't see anything before the limit. If you ask what is the spectrum of this operator, if you forget about this boundary condition, you simply consider n equal to infinity. So you have an infinite dimensional space. The spectrum will cover a whole region here. Every point will be there. And before the limit, you only see the curve. So these curves correspond simply to different values of a parameter g. This is g, which is 0 or slightly larger than 0. Then this bubble appears, and then this part disappears completely. You have a very nice circle there. OK, so this is one set of pictures. And this is a purely one-dimensional model. I want to show one more picture, which was produced by ourselves and is in our paper. From our paper, you see, sometimes it's very advantageous not to have a very good computer. It's better to produce a picture for 100 of these guys. You see, it's very similar to what you saw there, but there is some additional information there immediately from numerical point of view. You can see that the distances between these guys, they are very regular. They behave in a very regular way. And you can see that the distances here are very irregular. So there is a natural hypothesis immediately that if you want to prove something about the limiting distributions of these eigenvalues, then probably they should be roughly on not on an equal distance from each other, but on a distance which is described by a nice function. So this is another hypothesis.
Sorry, could you say again what the problem was that produced the first data that you showed with eigenvalues spread over the whole of the area of the complex plane?
The problem is this one. You simply look at this matrix. There is no physics behind that. You just look at this matrix, but you know, if you look at matrices which of full matrix, why not on a 3-diagonal matrix? And these are random variables which are independent of each other. They may have the same distribution. They may have also not necessarily the same distribution. That's what it produces. Say Gaussian.
Okay, so the difference is the randomness was in the off-diagonal.
Yes. It's not that much the difference, not that much the randomness. I'm going a little bit ahead of what I'm going to say. But the fact that they are not positive, say, or not all negative. They can be positive, negative, but there is some algebraic condition there which implies this dramatic difference of the pictures. Now, these are the same things for different distributions which were in our paper with Boris Haruzhenko, and at some point I probably should do it right now in order to show that I am not a very bad guy, and put in some references. So as I said, everything was really stimulated by this paper of Hatana and Nelson, another paper there, where they produced more nice pictures. And it took us by surprise, and I thought that this has to be explained, what is happening there. And these are the 4 papers we wrote with Boris. The last one was in 2005 in Israel Journal of Mathematics. And there is some work in preparation still. And this is concerned with the properties of the eigenfunction corresponding to these eigenvectors. OK. Now let me go a little bit further and show you even more pictures. I'm afraid I cannot find one of the transparencies, and I will write it. But the whole information is already there. So this is another picture produced by Hatana. And this is another one. Another one. I don't know how much you can see of it. Yes, it's possible to see them. And finally, this one. Yeah, I will explain it right now, of course. Now, this is, I shall leave this here. And I will explain. It is symmetric, as was noticed today. What? It is symmetric also in this way. And now, this is what David Nelson actually gave me, these pictures, when I gave a talk at Harvard. And I said, let's consider this model. Well, actually, this model, but now Q will be a matrix, say a 2 by 2 or m by m. So Q, I will look at the following equations or the following situation. I have Q1, Qn here, e to the power j times I, e to the power j times I, identity matrix. Here I will have e to the power minus ji, e to the power ji. And here I will have, of course, e to the power minus ji. This is Q2, e to the power minus j times I. I is an identity matrix. In other words, I consider the model which is a strip with periodic boundary conditions. And what is Q? I should explain what is Q here. Q is just a usual Q1 and so on, Qm, if the strip is of its M, 1, 1, 1, 1. In other words, it is a non-Hermitian model on a strip, and when I explained what are the results, I said it would be nice actually to have a numerical experiment. I actually draw these curves, but I draw because I never saw them from the experiment. I draw them like this. I said there will be something like this. There will be something like that. He said, yes, there is an experiment, and this is what it is. Anyway, let me now explain what I actually want to do here. I want to discuss these questions concerned with these curves. So these are the questions I would like to discuss. First of all, can one describe these curves mathematically, so to speak? Can one prove that they are really there? Can one write an equation for them? Is there a density function there? This is a question I already asked. You see that they are very nicely distributed, these eigenvalues on the curves. And there is a question, are the real eigenvalues actually real? And what about the spacing? And what about the eigenfunctions of these systems? So the usual questions you ask about self-adjoint case, you can, of course, and it is very reasonable to ask them here. And the features they have are sometimes very different from what we are used to. So there are several open questions which I already on the level of eigenvalues. I have already explained them. In particular, I would like immediately to explain one of these questions: are the real eigenvalues real? Which sounds a little paradoxical, but it isn't. You see, if I look at this picture, so okay, I see these eigenvalues there, but there are also some eigenvalues here. And usually what happens, you never see them outside the real line. The theorem we can prove actually tells that they will lie in an epsilon neighborhood of the real line. We cannot prove at the moment that these real eigenvalues actually should be exactly on the real line. And by the way, this is a theorem which is, well, it is certainly a right statement, but it is a probabilistic statement. Unlike the results concerned with the complex eigenvalues, some of them are not probabilistic at all. With a very small probability, you can have a picture where some of these eigenvalues will be outside the real line. However, this probability is tiny. It is smaller than exponential, I think. But there is no theorem about that. In the size of the system. It's a finite size system. In the size of the system. Exponentially small.
The real line, but a little bit outside.
No.
That's what you mean.
No. I put it in this way in order to stress the situation, to emphasize that there is a question there. But these are really on the real line. These are real. But to prove that they are real, this is the question. I believe they are real, and they are. This is a numerical fact. But I don't know the proof. Because okay, so how you go about that? How you control this situation? Let me try to explain that. So what you do, of course, you rewrite this equation in a usual way. First of all, you get rid of this g in the equation. So if you, it's a well-known, first of all, it is a well-known thing. There is nothing new there. This is immediate. And this is a similarity transformation. So if you write yk is equal to this thing, you immediately get this equation. There is no parameter now in the equation, in the main equation. The whole thing is shifted to the boundary conditions. By the way, I want to stress that the periodic boundary conditions are absolutely essential there. But I also want to emphasize that they are actually generic. They are the natural boundary conditions. I can explain it later if I have time for that, but right now I just want to emphasize it. Because without them, nothing will happen. You will see that these equations, if you have x0 equals 0, then you don't need this equation. It will simply disappear. So the problem will be, so the eigenvalues will be the same as in a self-adjoint problem. But once you have a slightly non-trivial boundary condition, from the point of view of this problem, the Dirichlet boundary conditions are very degenerate conditions, whereas the periodic boundary conditions are absolutely natural. They work both for the self-adjoint case and non-self-adjoint case. Anyway, this is what we get. Of course, we solve these equations in the usual way. We write this equation like that. We define the matrix which is a product of random matrices. And of course, we have immediately the notion of the Lyapunov exponent there. Once we have a product of random matrices, it is clear that this thing is going to play a very serious role in the description of the properties of the system. So how does this product of random matrices behave? Now, before I go to this, I would like to say that this trivial transformation actually implies the following fact, that z is an eigenvalue of the original problem if and only if e to the power nj is the eigenvalue of the product of matrices. So I think this is the first time when, well, I mean, it was some time ago already, but it is the first time when the eigenvalues of products of matrices started to play a serious role in the theory. I knew properties of the eigenvalues before for purely mathematical reasons, but they have never been used in the theory. Well, actually they were used, but in a very implicit way in the theory of products of random matrices, random Schrödinger operator, even in dimension 1. But here they really play a very important role because of the duality that we see immediately. So we see this equation, which is equivalent to our system of equations. And that is an eigenvalue if and only if e to the power nj is the eigenvalue of this product of matrices. This is the eigenvalue equation for 2 by 2 matrices, just that the 2 by 2 matrix is a product of these guys. So it's not a very simple matrix. Now, to control it, you of course need to know the asymptotic properties of the products of random matrices, and they are famously characterized by this number, which is called the Lyapunov exponent, and which is one of the definitions of these numbers is this one. It is a very short definition, but a very stupid one, because it doesn't tell you anything about the calculation of this thing. And we shall need a formula for the Lyapunov exponent, and for that there is a Furstenberg's formula. I will now explain what Furstenberg's formula is. It is useful to understand that, shall I try to use the other part? Can you see it well? It's not very well, huh? I don't know, I'm sure about. So what is Furstenberg's formula? You see, it has nothing to do with the original problem. And this is good, because it is an independent view on the product of random matrices. You have products of random matrices, IID, arbitrary size, m by m, say. They have to satisfy certain conditions. So independent, identically distributed, there is the so-called stronger reducibility condition. And of course, there is an integrability condition, which means simply, I forgot to put it in, is that the expectation of the log, yeah, also I didn't say they are with determinant 1, of the norm of A is finite. And the determinant is 1. So I forgot these two conditions there. And then you can always consider a Markov chain on the set of unit vectors. So here is a set S of unit vectors or unit sphere in the m-dimensional space. x1 you choose randomly, whatever the distribution first of all, at first. And then x2 is defined like follows. You take the matrix A1, apply it to x1, divided by the norm there is another vertical line missing here, norm of AX1, you get another unit vector. So you have a jump from one unit vector to another one. This jump depends, the distribution of the jump depends only on A1 and X1. It doesn't depend on the history. If I look at X3, it's only A2 and X2 that defines the distribution of the next step. So it is a Markov chain. I'm simply explaining what is a Markov chain. Of course, I'm going very far in my explanations, but the remarkable fact is that under the conditions I vaguely explained, there is a unique, oh, sorry, no, not a unique. There is for any invariant measure of this Markov chain, this number will be exactly the limit there. It doesn't depend on the choice of the invariant measure. It's a remarkable fact of Furstenberg's theory that this can be calculated or evaluated like this. And this means that in many cases, I explained it for the case when you have independent random matrices. In fact, this formula is valid for stationary matrices, but in this case, of course, instead of having a product of measures here, you will have a joint distribution of the pair vector and matrix. It becomes much more difficult to prove that in general that this formula will not depend on the choice of the measures. It's simply not true in general, and so on. There are all sorts of technicalities which arise, and they are sometimes very important. So we shall restrict ourselves to the case of IID matrices. But in principle, all of that is well developed and known, and it is a useful formula. So for us, it is important to remember that there is a formula which has nothing to do with the nature of the matrices of the way they arise. Okay. I'll need something else from this theory of products of matrices. This is a very brief review. Yeah, this is just what I said already, that Z is an eigenvalue if and only if e to the power n j is the eigenvalue there. Now, so what? We have looked at the behavior of this thing, but what turns out to be interesting is that this behavior depends very much on Z, of course. The Lyapunov exponent exists for every Z. That is fine. But the behavior of this quantity, if you fix this sequence Q there, an infinite sequence, then this number depends very much, or strongly depends on the parameter Z. And it is very interesting that it turns out that outside of the spectrum of the problem where G is equal to 0, of a self-adjoint problem, outside of the spectrum, this behavior for almost every sequence is very regular. Whereas on the spectrum, this behavior is horrible. So we remember that we are interested also in what is happening outside of the spectrum of the self-adjoint problem. Namely, when I say it is horrible, I mean the following, that if you consider the upper limit, which always exists by definition, and we consider the lower limit, that then with probability 1, the difference between these on the set of Z belonging to the to the real interval, which is to the spectrum of of the self-adjoint problem is strictly positive on the set which is everywhere dense on the spectrum of H0. And when I say H0, you may remember that there was an Hg there. I wrote it like that. G is the parameter. Now I can consider Hg when n is infinity, and when g is 0, the behavior of these Lyapunov exponents is really non-trivial on the spectrum, but it is very nice outside the spectrum. There is another thing which now tells you something about the behavior of the eigenvalues. And it turns out that these eigenvalues behave in exactly the same way and actually have exactly the same asymptotic behavior as the Lyapunov exponent. So you have matrices, you have the norms there, which you control by means of the Lyapunov exponent. But you also have eigenvalues, and they grow, which is not very surprising. The top eigenvalue grows exactly like the norm of the matrix. This is a typical situation. Of course, you can easily invent examples where the eigenvalue of a matrix is equal to 1, and the norm of the matrix is enormous. This is no problem to produce. But when you have products of matrices with decent behavior, I mean, with reasonable conditions on the distribution, this never happens. So these pathologies never happen. Okay.
So what's exactly the pathology?
Shmuel, namely with you, I discussed it a number of times. If this is the Lyapunov exponent, the averaged value, and this is the spectrum of the operator, then if you fix the sequence for every fixed sequence, in fact, you will see something like that. It jumps to 0 infinitely many times on every very dense set. This is the pathology. This is or whatever, the graph of the Lyapunov exponent. It is actually like this. I mean, quite often. So I have an immediate corollary there, you see. And the theorem, if you wish, that these curves, and let me show you the curves. I hope I can find them still. Yeah, I can. These curves, these two, are defined by this equation. Gamma of z is g. G is the parameter of the system. Okay. So what happens next is that, of course, you want to know a little more about the distribution of the, at least I promised that I will tell a little more about the distribution of the eigenvalues. I mean, about the fine structure of the complex eigenvalue. So the limit curve. I actually was not very precise in this statement. I said this is the limit, but this is the limiting curve already. Before that, you have a sequence of curves. Once the size of the system grows, which converge And you saw it on our picture where I had dots and I had also also had the limiting line. You see, here you have these dots. So these lines, they converge to the limiting line, which is given by this equation. So the distance between the lines is of order 1 over square root of n. So there is a central limit theorem, so to speak, here, which is governing this situation. But the remarkable fact is that once you are on the line, these eigenvalues, they move up and down. If they move up and down together. They still remain on a very smooth line. And this is what you see in the experiment simultaneously. So we have a theorem which I suppose I don't have on the transparency of Boris and myself, which was published in CMP some time ago in 2003, which tells you the following things, that if you look at these eigenvalues and nearest eigenvalues, say x or zk, let me call it zk plus 1. Then zk plus 1 will be equal to zk plus some function phi of zk. Phi will not depend on anything. It's a very nice analytic function of z divided by n. N is the size of the system, plus something of order smaller than 1 over n. In other words, well, more precisely, it will be of order 1 over square root of n. In other words, if you know one eigenvalue, I can, if I know this function, I can find all the other values using this formula. At the end, I will have an error of order 1 over square root of n, in fact. Of course, it may accumulate, but still, I will have the number of these eigenvalues here will be proportional to n on this curve. And by the time I reach this end, I will have an error of 1 over square root of n. So it's a very, very robust system. OK, so this is what I want to say about the eigenvalues. I already told you that we can prove that these curves converge, that, well, you may have many of them. I showed on one of the pictures there are several of them. And these, the only thing I would like to add to that in the case of dimension 1 at least, pure one-dimensional case, these properties are derived by some analysis using the Tauler's formula. One doesn't need real randomness there. We even introduced a class of potentials which we call self-averaging potentials. But all what we require is the existence of the integrated density of states. If it exists, you have all these properties. Now, if I want to tell more than that, if I want to say what is happening to the eigenfunctions, this is a much more delicate part of the story. You need to know not just the behavior, the law of large numbers for the log of the norm of this product of matrices, but you need to know this theorem about products of matrices, which is satisfied on the complex plane uniformly in Z. So there is a convergence to a Wiener process W of tz, depending on the parameter z, And this leads to a non-trivial conclusion about the behavior of the eigenfunctions corresponding to complex eigenvalues, only to complex eigenvalues. Let me go to the next slide. Oh, but we have the advantage of having the last talk. So nobody is in a hurry and everybody wants to know everything. Anyway, I'll try whatever I can. So from the theorem I just mentioned, what will follow is the following thing. That once you are in a finite system, the eigenfunction which corresponds to the complex eigenvalue strictly away from the real line will behave like that. It will be localized. The decay here will be minus square root of n. It's not exponential localization. It's localization minus with a speed minus square root of n. Once you are in the limiting system, you will never see it. So it disappears in the limit. What is actually happening is the following thing, that for this particular eigenvalue, or the eigenvalue which is nearby, there is always an eigenvalue nearby. When you change the system, you of course get all the eigenvalues which have nothing to do with, well, roughly speaking, nothing to do with the previous set of eigenvalues you had. But there is the nearest one which is there, and you can ask a question about this eigenfunction. But what will happen is that this maximum, once you normalize it, will simply run away to plus infinity or minus infinity. You will not see it in the limit. So this is why numerical analysis sometimes are misled. They think that you will have delocalized eigenstates in a finite box. Never. You will never have delocalized eigenstates in a finite box. They will always be localized. You take 10 to the power 23, the beloved number of atoms, and they still will be there. 46, still there. Whatever. But once it is infinity, they are not there. You don't see any of them. Okay. Actually, my talk was about the strip. And I will tell several things about that. You see?
Try to be concise.
Oh, sure, I will. Very hard. Don't worry about it. So this is now the system where you have m by m matrices. In my example, these are, on my picture here, these are 2 by 2 matrices. These are the QKs I wrote. I actually draw them there. You can have, again, in this case, you have to define two Lyapunov exponents, gamma 1 and gamma 2. There are, similarly to what we had before, there are formulae for them. You can extend Furstenberg's formula to the gamma 1, to gamma 1 plus gamma 2. You cannot directly have gamma 2. And then, of course, you have the equation for gamma 2. And these are the equations for the eigenvalue curves you saw on one of the pictures. This is gamma 2. The outer curve is gamma 2 of z is equal to g. The inner curve is gamma 1 of z equal to g. And you will have exactly the same properties here and here, just that they are much more difficult to control because there is no Tauless formula there. There is no proper analog of the Tauless formula. And this makes our analysis for pure one-dimensional case for these eigenvalues, I mean, relatively simple, whereas here you need to use the full strength of the theory of products of random matrices. Okay, I think I have finished. Thank you very much for your attention.
Question, please. Please.
I'm not sure what you're saying in this case. I mean, you have an n by n matrix, but you only seem to have two curves.
M is 2.
This is the case when I have a 2 by 2 matrix. If I will have m by m, I will have m curves, of course.
Okay, good.
And this, I simply draw the picture for the case of 2 by 2 matrices. And this is the only case when I saw the results of numerical experiment. But I can tell you, this is the full truth. I draw it before I saw them. This was a theoretical prediction, not so. And Hatana, who actually saw these curves, I don't know why, he actually didn't show me the curves. He saw it before Nelson.
More questions? Please.
So in this problem of non-Hermitian Hamiltonians, so you show this Hatana Nelson as motivation, and they had some sort of physical motivation for it. So
They do, yes, they.
can you say in this physical motivations, so what would be quantities that one should sort of think about as sort of
No, you better ask them what the quantities there. I will not say anything about that because I'm not a specialist in that. I didn't have the time to really understand it. I read it. I will not repeat the words without, serious understanding of what they actually want. For me, the motivation was a very strange phenomenon. I first couldn't believe it. I actually, when Boris came to my office and said, I told him, first you find the physical paper where this is interesting. So he found it and said to me, there are smooth curves there. I said, this is impossible. This cannot be the case because I knew already then, I knew it because I know this theory of self-adjoint operators. And once you have a point, you have a line there in the spectrum. So this is how the spectrum is in the limit. So how can it be that before the limit you only see these guys, and 2000 is already a lot? You only see that, and so I simply couldn't believe. But when I saw the curves, I thought it cannot be wrong, because such a nice picture cannot be produced by chance. So, and indeed it isn't. So this was the motivation. So it was basically mathematical. I probably should say that we also proved that the initial problem really has the limit. The initial problem I started with, and this is another paper which I mentioned there, but only it was on the list, but nothing else. Yeah, as usual. So the initial problem, which was this one, we actually proved that these limits exist. But at the moment, this is a very different proof. I mean, different from the one we have there for the Hatana-Nelson model, or Hatana-Anderson model with non-self-adjoint Anderson model. In this case, again, the existence of this limit actually follows from the analysis of Lyapunov exponents. There is the so-called Widom criteria, and in order to use it, you need to know again something about the behavior of Lyapunov exponents, and if you know, you can conclude that this limit exists. It is a two-way movement. If you know the Thouless formula, you can control Lyapunov exponents, and you can control all these equations. It's very nice. If you know a lot about the Lyapunov exponents, you can control what is happening in the system, and you actually can prove the Thouless formula there. So there is also a Thouless formula in this case. But it is not used for anything. It is just proved there as a corollary of what we did for this system. I didn't have any time to.
You mean that you proved two-dimensional density or density on the line?
You proved the following statement.
There is a limiting
That there is a limiting distribution. In particular, if there is a density on the line, there is a density. It's in a weak sense. You do not control separately the line, which I would love to know how to do. There is no, at least I don't know any approaches. I know how to prove probably that the eigenvalues which are real are really real. I probably know that, I think.
Sorry?
But I don't know that. Why these eigenvalues are real in this problem. That's a very different story.
Another question?
In various conversations, you've said that in your discussion today, you have the off-diagonal elements of e to the plus g and e to the minus g, which obviously have the same sign. But when the off-diagonal elements above and below have different signs, one positive and one negative, you get quite different behavior.
That's what you get.
Can you give me a physical explanation?
Physical explanation.
Yeah, physical explanation.
What should I call a physical explanation?
Qualitative.
I mean, why should you expect that before you've proved it?
No, there is a mathematical explanation in the sense that when you make, but I wouldn't call it physical ever. When you have random numbers on the, I don't have, okay. Where is this show? If you have this picture, if you have this matrix and you have a diagonal here, and you have something there and something there. So what happens when you want to do some manipulations with it, to use the similarity transformation in order to get rid of too many parameters there, you need to have the product of these two guys, which is positive, because you take the square root of something. Otherwise, you end up with a non-existent transformation. That's what you have. So mathematically, it is clear why it is happening. It's a very simple thing. But I don't know any physical explanation for that, neither would I imagine what it would be.
Okay. Okay. Then last question.
Okay, when you have several curves, those are described by the equation gamma of v equal the parameter you put in the boundary condition. Is it?
You have this matrix there.
Okay, where gamma is the Lyapunov exponent.
No, you don't have one Lyapunov exponent. You have several of them.
Of t
You
delta.
have these equations. They are separated from each other. These are independent equations. Gamma j of z is g. G is the same parameter as before. You have matrices like that. Q1, you have e to the power g I. Of course, you can have a more complicated structure there. There will be a more complicated equation. But in this case, this is what you have. You have m of these equations, g between 1 and m. If the matrices, these matrices are m by m, of size m by m.
But is it true for Anderson model that gamma is equal to the real part of exponent of transfer matrix? I mean,
Gamma
arises from
Which gamma? You see, you should realize that there is not one gamma, there are several of them.
several gamma. Those are come from diagonalization of T dagger S dagger S, as you call it, transfer matrix.
Okay. So there are several of them there,
Okay.
yes?
If you diagonalize S and not S dagger S, you have, also in this case, you have exponents.
These will be the exponents of the eigenvalues. What you are saying now are the exponents of the
Asking whether
eigenvalues.
the real part
And
is-
they will behave exactly like these guys.
So, okay.
Okay. Let us thank you.
Thank you.